Okay, today we're talking printing pages. Now, we've all got printers connected to our computers, and when we want to print something, a page comes out like this, not this big, but it comes out like this. And typically you'll notice there are margins. So we've got the printed area inside, we'll represent that with the grey area, and then we have margins around that where there's no printing. So for this particular example, we have margins left and right. We have a margin of 1 centimetre on the left and 1 centimetre on the right. And top and bottom, we have 2 centimetre margins, respectively. So what's our outcome? Well, our outcome eventually is to maximize the dimensions in such a way that the printed area is maximized. What does that mean? Well, it means basically that we have a set area for the page. The total area of the page, x times y, is 288 centimetres squared. Now, we still have those margins inside, so what we want to do is maximize the printed area. Now, to maximize the printed area, we need to have certain dimensions, a certain y and a certain x. So that's eventually what we're after. We're going to use differential calculus to find the best dimensions of y and x. So for now, part one, what we're after is coming up with this formula. So before we do any differential calculus, we need to come up with a formula to maximize the printed area. This is the printed area, the grey area here. That's what we want to maximize. This is the formula. So how do we come up with that? That's what we're going to do now. And then eventually, we're going to find what the dimensions need to be in order to maximize that area inside. So let's do this. How do we come up with that formula? Well, the first thing we want to do is look at what we got. So what do we have? So as I look at this, I can write down, well, we know that the area is 288 centimetres squared, the total area. So let me write that down. Area equals 288 centimetres squared. But what we're after is the printed area. So, area, and I'll put a little p there to represent the printed area. Now, what does that equal? Well, that equals, well, let's have a look here. We have x across here, and we have a centimetre there and a centimetre on each side of the margin. So that's 2 centimetres that we take away. So that means we're going to have, for this part here, x take away 2. So it's x take away 2. And vertically like this, along the height, we have y, and take away 2 from here and 2 from there. That's going to be 4. So that's going to be y subtract 4. So that's the area of the printed inner grey part right there. So that's a printed area. So how can we incorporate these together? Well, we know that the total area is A equals xy. Now we can't differentiate A because we've got two variables there. It's an x and a y. So we've got to put it in terms of one thing. Same with this, we've got an x and a y. So what I'm going to do is I'm going to make y the subject here and then drop it into this y and replace this y. So let me go ahead and do that. So area equals 288 and that equals xy. So therefore I could say this. I could go 288 equals xy. We can make y the subject. So y equals 288 divided by x. Okay, let me put a little border around that. Okay, the x and y again that's the total y there and the total x there. That's what we've got right over there. So why don't we go ahead and drop that into here and replace it with the y there. So we're going to replace this y with that y. So we're going to drop it in there. So let's go ahead and do that. So now we're going to have area of printed equals x take away 2. And then the y becomes 288 on x. X subtract 4. There we go. Now all we have to do is expand this using the FOIL method. So area of printed equals x times 288 on x, so that becomes x times 288 all over x. And then we have x minus 4, so that's minus 4x. Then what do we have? Then we have a minus again. We have minus 2 times 288 on x. So 2 times 288 is 576. So that'll be 576 all over x, because the x is still there. Okay, and then we go negative 2 times negative 4. That's going to be positive. 2 4s are 8 plus 8. Okay, let's further simplify this. We can cancel x's top and bottom from here, there and there. So that leaves us with area, the printed area, equals 288 and minus 4x minus 576 on x plus 8. We can take the 288 and add the 8 to that. So altogether, that's going to give us 296. So area of printed equals 296. Let's bring the minus 4x. And then we have a minus 576 on x. And there we go. Let's match it up. Does that match 296? Yes, that matches. We have a minus 4x. That matches. And minus 576 on x. That matches. We have a match. So now we have an expression that we can eventually differentiate. So we can maximize the area of the whole page, so the area of the printed page is also maximized. So that's that part. I'm about to do part 2. We're about to differentiate this part over here, this formula right there. Okay, now we're going to find the dimensions x and y, what they need to be in order to maximize the printed internal area there. So in order to do that, we need to find the first derivative of this expression. Now, in order to do that, we need to write it in a differentiating friendly format because we have 576 over x. That's hard to differentiate. So I'm going to bring it up next to it and put it to the power of negative 1. So area equals 296 minus 576 x to the power minus 1 minus 4x. Okay, that looks a lot better. So now what we're going to do with this expression is we're going to differentiate it and then make it equal 0 to see if it's a max or a min. So let's do that. Area equals, let's see, differentiating negative and a negative becomes a positive. So that's going to be a plus 576 x to the power of minus 2 minus 4. We're going to make it equal what? It's the first derivative. Let's make it equal 0. Equaling 0. Let's bring the 4 over the other side, over here, to make it a lot easier to work with. And also, let's bring the x back underneath so we can manipulate it easier. So we've got here 576 all over x squared. That equals 4. Let's multiply both sides by x squared. And that's going to bring the x squared over that side. So we're left with 576 equals 4x squared. So now we just divide both sides by 4. Let's divide both sides by 4. 576 divided by 4 gives us a grand total of 144 equals x squared. Square rooting both sides, therefore x equals 12 centimeters. So that's that x there. That's one of the dimensions that we've got there. So let me just put a border around that. All right, that's one of the dimensions. Now, before we find the other dimension, let's check and see whether it is, in fact, a maximum. And the way to do that is to find, of course, the second derivative. So let's go ahead and do that. So a double dash, or dA dx, because we're differentiating with respect to x, or d2 with x. So I can just put 2 primes there, equals negative 2 to the front. 2 times 576 is negative 1152 x to the power of minus 3. We drop the power by 1. So that's that. The 4 disappears. So that is our second differentiation. And as you can see, if I take a positive number like 12, there's our 12, drag and drop it right there for x, it's going to become negative. Why? Because we have a negative in the front there. So therefore, this value here of x is going to be, well, it's less than 0, which means it's going to be a maximum. So that confirms what we want. That dimension x will provide a maximum area inside. So now that we have that, we can go ahead and find the corresponding y. Now you may recall from part 1, we had this expression here, y equals 288 on x. Where did we get that? We got it from here. The area of the whole page is 288. So we make y the subject. So let's find y now. So y equals 288 divided by x, which is 12. 288 divided by 12, y equals the dimension all the way up there for the whole page is 24 centimeters. Okay, we have the dimensions. These clearly are the 2 dimensions, x and y, so that we could maximize the printed internal area with those margins.